We were discussing the basically the measurement of large resistance, high value resistance, and you can say that insulation resistance. And we discussed in the last turn loss of charge method. If anybody is having any question regarding this method, this is considered as the main and the most accurate method or popular method for measurement of large resistance. This is called loss of charge method. This kind of circuit arrangement is used. Charging and discharging of capacitor is basically used for measurement of resistance. So if anybody is having any question regarding it, you can ask. Otherwise, the last method is mega ohm bridge. So um, first of all, I think I hope that my slide is visible to all of you.
Yes, sir.
So if again we are trying Wheatstone bridge for measurement of large resistance, because measurement of medium resistance, in measurement of medium resistance or moderate range resistance, Wheatstone bridge is the best method. So we'll see how will it perform when we are using it for the measurement of without any modification for measurement of large resistance. So here large resistance is shown as a terminal resistance. A and B are the main terminal, resistance terminal, and G is the guard terminal. You know, guard terminal, guard resistance or guard arrangement is used to to take care of leakage current, that is potential cause of error in case of high resistance measurement. So we treat high resistance as a three terminal resistance. Two are the main terminals of the resistance, and one is your guard terminal. So why this guard terminal is so important? Because you see the resistance between guard terminal and the main terminals of the resistance are significant. Means if the guard terminal is not connected properly, then the resistance will have significant effect on the mean resistance as far as measurement is concerned. So in this case, you see this guard terminal, because this resistance between main terminal and the guard terminal is insulation resistance, and it is of the same order as the unknown resistance, because your unknown resistance belongs to the high resistance category. So suppose I'm taking equal, means your R is also 100 mega ohm, and your terminal resistances, sorry, your resistance between the guard terminal and the main terminals of the resistance are also 100 mega ohm. Now we are using this high resistance using Wheatstone bridge. Here you see Wheatstone bridge. So obviously we will measure our and measured value. Obviously here, if you look upon the circuit, equivalent circuit of the unknown resistance, so these two are basically in series, and this series combination is in parallel with it. So equivalent resistance is, which is appearing in this arm, is basically 67 mega ohm, although the unknown resistance is 100 mega ohm. So there is a error of 33%. We are trying to, because when you will take the P upon Q into R upon S, and then you will measure the value of unknown resistance using balance equation after balancing the bridge, then you'll end up in measuring 67 mega ohm, because you see this because here in this arm we are not putting 100 ohm, but we are mega ohm, but we are putting this 67 mega ohm resistance here. So that's what is the issue, and that's what problem you will face if your Wheatstone bridge is not properly modified to connect the guard terminal at the appropriate place. So this is whatever issue that I had discussed here. Is it fine to all of you? If anybody is having any query about it, you can ask, please. You're not having any issue. Okay. Now the solution is here. In this case, what is done basically, इसको बंद कर दो भाई सही से. What is done here? In this case, this guard terminal is connected uh, to one of the galvanometer terminal here, and obviously, when you will do that, then this resistance will come in parallel. This is connected in parallel with P, and this resistance is connected in parallel with the detector. So resultant circuit is this. This is nothing. This is nothing. So resultant circuit is this. So when we talk about the, now we talk, because this is 100 mega ohm, this is 100 mega ohm, this is 100 mega ohm. So we are interested in finding out the value of R, not the RAG and RBG. So you can see with this connection of the guard terminal, these resistances, the resistance between guard terminal and the main terminal of the resistance are basically, and now they are connected across the P and across the G. You can look, this G's will appear across this, RBG will appear across the galvanometer, and RAGs will appear across the P. So what will be the effect on the measurement? Again, we will try to find out. Now suppose, so as far as the means, when you will balance the bridge, obviously this resistance, the terminal guard resistance, will not have any effect on the bridge performance because it is not appearing in the picture. Because once your bridge is balanced, then this circuit is only affecting the resistance of the galvanometer. So that is all it is doing. Otherwise, it is doing nothing. Means once your bridge is balanced, this branch is out of picture. Even if it is not balanced, again this particular modification is not going to affect the performance of the bridge. It only affect the amount of, for a particular degree of unbalance, amount of current that will flow through the galvanometer, because overall resistance will be altered. Now only problem, the means the effect on the bridge performance will be because of this resistance, which is appearing across the P, and obviously this will modify your value of the P. So how much the effect will be, the error will be, because we don't know, we are not counting this resistance. We are aware of P, we are aware of Q, we are aware of S when the bridge is balanced. So by this bridge balance equation, R is equal to P upon Q into S, will calculate the value of R. But because of this connection, this resistance is RAG is appearing across the P. So obviously value of P is modified. And if we are not aware of that, we are not able to find out that, then that much error will be present here by the value by which your value of P is modified. Now we'll see how much effect in a typical example which we have taken. Suppose RAG is 100 mega ohm, that is already there, and P is 100 kilo ohm. So really P and Q, we are free to choose the value of P and Q. We are not required to have a same, it should be in same range of that of A. So P and Q, whatever ratio P and Q will have, if R and S will have same ratio, bridge will be balanced. So obviously, generally we require standard variable resistance in the range of unknown resistance to balance the bridge. P ratio arms are independent of that. So suppose P is 100 kilo ohm. Now I want that you should calculate what is the modified value of the P when we are having these two resistances in parallel. बताइए भाई जी, आपको कुछ करने को बोल रहे हैं, आप उसको कर लीजिए. So this is your P dash basically. So what is the value of P dash? Where P dash is basically the 100 kilo ohm and 100 mega ohm connected in parallel. What is the equivalent resistance? इसको calculate करिए जल्दी भाई. I want that you should calculate and let me know. In the meantime, you respond your roll call. Few of the student I'll take. Roll number 1, roll number 2, roll number 3. So if you look upon this value, so what is the value of original value of your P is 100 kilo ohm, and the equivalent resistance is coming out to be 99.9 kilo ohm. So now in this case, even if we are not changing, we are not because this resistance is not easily measurable. So if even we are not including the effect of this modification, we will get only error of 0.01%. You understanding or not?
Yes, sir.
Instead, we are taking here 100 kilo ohm to calculate the unknown resistance, but actually it is 99.9 kilo ohm. So earlier when we were not connecting it that way, then we are getting the error of around 33%, and now it is reduced to 0.01%. So this particular concept is used for mega ohm bridge, and a typical mega ohm bridge has shown here. You can see that obviously this is not an easy composition, because very high value variable standard resistance is very costly. So generally it is not preferred. But in any case, if in certain testing laboratory, you may find means if you know what it should be the value of insulation resistance, and then you can have only one value of standard resistance. So in that case, if it is varying from that value, obviously it is not confirming your insulation resistance is not confirming that it is having a desired value of resistance. So accordingly, quality control or health monitoring is done, or testing, you can say. So this is a typical mega ohm bridge, and the concept on which it works, that I had already described it here. So this is the last topic of this unit. So in this unit, we discussed different method for measurement of resistances, and means on the basis of measurement, then your whole lot of resistance values are divided into 3 parts. One part is your low resistance, that is less than 1 ohm, and then medium, that is the most you can say moderate range, that is 1 ohm to 100 kilo ohm, and beyond 100 kilo ohm is the high resistance. And we discussed methods used for it. Means the methods which we are using, it is like that the most easiest part from the measurement point of view is the medium range, moderate range. So 4 method we have discussed, that is voltmeter ammeter method, substitution method, and Wheatstone bridge method, and ohm meter method. And then extreme methods are having their own challenges. So we discuss low resistance measurement, where the lead and contact resistance is a challenge. So then over there, modified voltmeter ammeter method, and then Kelvin's double bridge and potentiometric methods we have discussed. And Kelvin's double bridge is considered as a best method. And then in high resistance, your leakage current is one of the potential cause of error, and using guard circuit we can take care of it. So as far as high resistance measurement methods are concerned, so it is direct deflection method, then loss of charge method, and mega ohm bridge that I discussed today. So all these things we discussed here, and with this knowledge you can read any literature based upon the measurement of resistance, I hope that you will be able to understand. And the issues that is discussed over there, you will be able to comprehend. This is what I was the outcome I tried to you have. So anyway, I'm finishing it today, and I'm starting your next unit, that is unit number 2. So if anybody is having any query at this point, you can ask, otherwise we'll move forward. So as usual, you are not having any query. So I'm going to unit number 2. Unit number 2 is about AC bridges. So in unit number 1, we have discussed about measurement of resistance. And as in the starting itself, I told you that measurement of resistance is very resistance is a highly measured parameter if we compare it with the other electrical circuit parameters, because in a lot of application resistive sensors are preferred and used, and they solve the purpose of measurement, and all these methods are used accordingly. So that's why you can see that one whole unit is dedicated to measurement of resistance. And as far as the measurement of AC bridges are concerned, so it is basically measurement of inductance, measurement of capacitance, measurement of frequency, measurement of mutual inductance. All these things we'll discuss in this unit. So using AC bridge method is considered as a standard method for measurement of inductance, capacitance, and mutual inductance and frequency. So we'll start the AC bridge. AC bridge is, from circuit point of view, AC bridge is similar to the Wheatstone bridge. It is like Wheatstone bridge. It is also most of the AC bridges. It is also having 4 arms, and instead, because it is AC bridge, so excitation is AC. So in this case, we can use all 3 components. Means in the bridge arm as a bridge arm component, resistance, inductance, and capacitance. So that's why you can see that here your impedances are used instead of resistances. Impedances are having relevance, but because of whatever things that has been appended into the AC bridge is AC bridge circuit is much more complex circuit than the DC bridge, although the circuit arrangement is similar, but despite of that, your AC bridge is more complex, much more complex. And how it is complex, I'll discuss today itself. Now, one more thing I want to tell, it was in my mind. Anyway, so AC bridge is much more complex. Now, one more thing I want to tell you, that since it is possible to use all 3 electrical circuit components like resistance, inductance, and capacitance, so different type of bridges are proposed, and we can have more than one type of bridges. So there are many types of bridges. By having different combination of resistance, inductance, and capacitance, we can have different type of AC bridges. So there are many types of AC bridges we'll discuss in this unit. Some of the AC bridges are good for measurement of inductance, some of them are good for the capacitance, some of them are good for the mutual inductance, and some of them are good for frequency measurement. All these are possible. And so now we'll discuss first of all bridge balancing, on what is the meaning of bridge balance here in AC bridge, and what is bridge balance equation. All these things we'll discuss. So bridge balance concept remains same here also, that your bridge will be balanced only when the potential across the detector arm will be equal. So whenever it will, for whatever set of values of Z1, Z2, Z3, Z4, it will become equal. The potential across the potential difference across the detector becomes zero, or potential of the detector arm, two arms of the detector or detector terminals becomes equal, then your bridge will be balanced. So under that condition, obviously, I1 into Z1. So these equations are not scalar equations. Now, in the case of AC, these equations are basically your complex numbers. Your I is also complex number, your Z is also complex number. So although I'm writing it simply, but it is having two parts. Every equation will have, every side of the equation will have two parts. It will have real part and it will have imaginary part, if we are working in the um, rectangular representation domain. And if it is worked in a if we are representing them in the polar form, then obviously we'll have the amplitude part and we'll have the angle part. So anyway, so here I'm trying to derive the balance equation. So here you can see that this will be, because your bridge is balanced, so your I1 will be E upon Z1 plus Z3, and I2 will be E upon Z2 plus Z4. And then finally, we are having these equations. Then after simplification, you see we got Z1 into Z4 is equal to Z2. This is the balance equation, like P upon Q is equal to R upon S, that kind of. But here, now you see that although it looks like, that's why bar is there on the head. So these are the complex numbers. So although it seems that it is a single equation, but it is not single equation, it is two. So in the case of AC, we have to satisfy the resultant two balance equations simultaneously, and that makes the difference as far as the complexity is concerned, and as far as the difficulty in balancing the AC bridges are concerned. uh, Balancing AC bridges are much more difficult than balancing the DC bridge, your Wheatstone bridge. So anyway, now I'll show that how this single equation represents the two equations together. So if we are representing Z1, Z2, Z3, Z4 in polar form, so you see that it is in polar form. So balance equation will be the amplitude as well as angle should satisfy these of the components that your impedances you are using. Only then your bridge will be balanced. Means your amplitude part, amplitude balance equation, and your angle, phase angle balance equation, both of them should be satisfied simultaneously. Now I took, although it is all hypothetical, I took four resistances, four impedances. In general, I considered them as a inductive. It is all hypothetical. It's not real bridge, but I just want to show one thing, that what will be the final outcome. So this is your balance equation. When we will multiply them, and then we'll simplify, and then we'll segregate, then you can see left side we are having real and imaginary part, and real and imaginary part. At the right side we'll equate both of them. Now you see, this is here you can see that we are getting two equations instead of one balance equation. We are getting two balance equation made up of the bridge arm components. And when these two equations are satisfied simultaneously, only then you will have your bridge will be balanced, actually balanced. And to to achieve this requirement that is associated with all the AC bridges, because of this reason, your AC bridge balancing is not an easy task. It is a difficult task. When we compare it with, it is not that it is not possible, but balancing the bridge is AC bridge is difficult in comparison to the Wheatstone bridge. So now we'll discuss different issues associated with the AC bridge balancing. Sliding balance is one of the problem. I want that you listen very carefully, although it is written in the book also, but you may not be able to understand this issue when you will read your book. You concentrate. I'll try to make you understand. So sliding balance problem is one of the issue that is present in AC bridges only. It is not present in the DC bridge. So what is that sliding? And this makes your life tough when you are balancing your AC bridge. So what is this and how can we tackle it? What is the solution to avoid? All these things we'll discuss. Although it is not necessary that that solution is applicable all the time. There are many constraints. When we'll discuss all those things, practicality of the situation we'll discuss all. But I'll try sliding balance problem. I'll try to make you understand with these two balance equation. All those are situation is all hypothetical. Now in this case, you see that these two equations are not independent balance equation. What is the meaning? Meaning is that we are having generally what happens. We are required to have certain to balance the bridge. We are required to have certain bridge arm components, variable components. Like suppose in this case here we are having inductance and resistance. Here also we are having so suppose your inductance, we made the inductance variable in this arm and and resistance variable in this arm, so that by varying these components we can balance the bridge. Like in AC bridge, one of the arm is your standard variable resistance, so that arm will be manipulated or varied to balance the bridge. Similarly, we require here also. So obviously in most of the cases you will see that instead of one component, we use two components. That is the requirement. So generally, so suppose we are having x3 variable and r4 variable to balance the. So if we are talking x3, so you can see that x3 is available here as also in this balance equation, and x3 is available in this balance equation. Now if we talk about the r4, so r4 is available in this balance equation as well as in this balance equation. So such kind of balance equations are called dependent equation, where the variable components are present in both the equation, one variable component or both the variable component. So when we are having such kind of situation, then sliding balance problem occurs. What is the sliding balance problem? Suppose for one set of values of r4 and x3, for one set of values of r4 and x3, suppose this equation is satisfied, but this is not satisfied. Now we varied again. Now for another set of r3 and x3 and r4, this equation is satisfied, but this becomes unsatisfied. So this situation, because you're trying to satisfy both the equations simultaneously, but you are searching, you are varying r3 and x4, sorry, r4 and x3, but sometime one equation is getting satisfied, other is another, and then other is. So this particular problem is called sliding balance problem. Are you understood? Because you're not able to satisfy simultaneously for both the balance equation, and this will cause sliding balance problem. And sliding balance problem is because of the independent balance equations. Is it fine to all of you?
Yes, sir.
Yes, sir.
Now solution is, we are required to make them independent. Means your one equation should have one variable component, and other equation should have another variable equation. So concept is, suppose your r4 is present only here and your x3 is present only here. In that case, you should have such a balance equation. If it is possible, then these two balance equation will be independent. So R4 you can use to balance this equation, and X3 you can use to balance this equation. This way, sliding balance problem can be avoided. This problem will not be present when you are having independent balance equation. So what is the meaning of independent balance equation? Means what is sliding balance problem? And with the independent balance equation, we can tackle this sliding balance problem. And how can we ensure that how can we get independent balance equation? That solution is also here, that if we are having both the variable component in the same arm, like in this case, if we are having R4 and X4 variable, or R3 and X3 variable, if this is there, then we can have independent. That I'll show when we'll discuss the um, we'll discuss the real practical bridge circuit. Then I'll show you. It is not possible to show it here. So I'm summarizing all the things. Sliding balance problem is common in AC bridges, and this makes difficult to bridge the balance, to balance the bridge. And this is because of the independent balance equations. And when your variable components are present in both the equations, one variable or both the variable components are present in both the equations, then if we are set of values of the variable components, if we are satisfying one equation, then other is getting unsatisfied. And when we are, so this is a common thing that happens, and this leads to the this leads to the difficulty in balancing the AC bridge, and this problem is called sliding balance problem. Sliding balance problem can be resolved using independent balance equations. When we are having, what is the meaning of unbalanced equation? One of the variable is present in one equation, balance equation, and other is another balance equation. Then we call both that balance equation are independent to each other. So by varying one variable component, we can balance one equation, and by varying another balance. So this, how can ensure that we should have the independent balance equation? So we are required to have variable components from same arm. Like in this case, if we are having R3 and X3 variable, or R4 and X4, so this will means and I'll show you this thing. Whatever I'm saying, that we will get verified when we'll discuss the practical bridge. So this will ensure you the independent balance equations. So all these things that I discussed in general with reference to the AC bridges, without referring to any specific AC bridge, that AC bridges are more complex circuit in comparison to DC bridge. And since in AC bridge excitation is AC, so we can have many components, different components like resistance, inductance, and capacitance in the arms. So the many type of AC bridges are possible. And as far as the balance equation is concerned, we have similar balance equation, but only instead of resistance, here we are having impedance. And because of the impedance, instead of one balance equation, we are having two balance equation, and that is shown here. Generally we work in the polar form, so in a rectangular form, so that's why I'm showing this. And then we are having sliding balance problem because of having two balance equation, and when these two balance equation are not independent, then we'll have a problem of sliding balance problem. And by making these equations, balance equation independent, we can avoid the sliding balance problem. And for making it independent, we are required to choose both the variable elements in the same arm. So this is all which I discussed. Although the solution that has been told here, in many cases there are many other requirement also, accuracy and economy. So you will find many times this, despite of having a choice to have independent balance equation, but we prefer dependent balance equations, and sliding balance problem, because other things are more important, like accuracy and economy and resource requirement. All these things are there. So that's why we'll discuss all these things. So if anybody is having anything, any doubt in whatever I have discussed here, you can ask. Otherwise, we'll start discussing different type of AC bridges. Many type of AC bridges we'll discuss in this unit. Although this unit is bit monotonous, because same thing we'll discuss again and again, but you have to bear with me. I'll try to make it as interesting as possible. Should I move ahead?
Yes, sir.
Okay. Now, one few more thing. Here you see generally in excitation, oscillators are used at different frequencies, 40 hertz to 125 kilohertz. Power output is 7 watt, and in general 1 kilohertz of oscillator with the 1 watt power is used, means general. And here you see detectors are not galvanometer. You cannot use simple galvan because there is AC supply, so that won't work here. So headphones are used. Means if your frequency, excitation frequency is in audio range, then we use headphones. Then vibration galvanometer is very common choice, general choice. It vibrates, and when it settles to the null zero value, then we say that. Then tunable amplifier is also used, means the amplifier which is tuned for the frequency, excitation frequency, that is also used. So these are the things, specification, you can say different components. Now I'm coming to different type of. Now these bridges means I try to divide this chapter into measurement of inductance, measurement of capacitance, and measurement of frequency in this form. So these bridges, you can see that although their application is same, measurement of inductance, but many bridges people have proposed, and all these bridges are having their own pros and cons. So we'll discuss everything. So we'll starting with the Maxwell's inductance comparison bridge. So all these bridges are used for measurement of inductance. They are good for measurement of inductance. So this is the circuit of Maxwell's inductance comparison bridge. So here you look, it is having 4 arms, and the first arm we are making it unknown arm. Means this, here we are having a coil whose resistance is R1 and inductance is L1, and we want to measure resistance and inductance. And obviously bridge will give you we'll be able to know this value in terms of these other 3 arms. So another arm is having, you see, variable inductance and variable resistance. We require these two standard variable inductance and resistance to balance the bridge. Then we are having resistance in 2 arms, remaining 2 arms. So the method means, first of all, in all bridge cases, we'll try to derive the balance equation, and from balance equation we'll try to find out its application. So application is measurement of resistance and inductance of a coil. So method is very important. This same method will follow throughout this unit. Means method means steps I'm talking about. And if you follow these steps, although these steps which I'm emphasizing here, it seems very trivial, but you'll find if you're not follow, this is my experience, although it seems very trivial here, but in examination, despite of being trivial, many mistakes you commit if you're not following a particular steps. So first of all, whenever you are dealing with the bridge circuit, then you draw the bridge circuit. It's the best strategy. And then you write the arm impedances. You see, I had written arm 1 impedance R1 plus j omega L1, arm 2 R2 plus j omega 2 L2, R3, Z3 is R3 and Z4 is R4. So this way you should write. Now balance equation, you know this Z1 into Z4 is equal to Z2 upon into Z3. And now you write these equations here and then you simplify. Means at left side also you should have real and imaginary part, and right side, and then you equate real and imaginary parts separately. So you can see that we are having two unknowns here, and here we are having one equation. But if we'll equate real and imaginary parts separately, then we will have two equation, and from these two equation we can find out the unknown value in terms of the known bridge, known components of the bridge. So here when we equate the real part, so we got the equation expression for measurement of R1, and when we equate the imaginary part, then we got the equation for measurement of inductance. So this way we are able to derive the bridge balance. These equations are called, this equation and this equation are called bridge balance equation. So if anybody, if before discussing any other thing, you try to look upon this, and if you are having any query, you can ask. By the time I'll take your attendance, remaining students. Respond your roll call, please.